Welcome to the fourth session on moment distribution method and myself Vahiniyam of GEC Haveri. So in the continuation of analysis of continuous beams without sinking, so today we will consider a continuous beam with an overhanging portion. So in this ABCD is a continuous beam where A is a fixed end and CD is overhanging portion. Okay. So let us consider an overhanging continuous beam. So the first step is to find the fixed end moments. So AB is subjected to UDL throughout. Therefore, the fixed end moment MFAB is calculated by using the relation minus WL square by 12, which will be equal to minus 20 is intensity of UDL and 8 is span of the member AB. Minus 20 into 8 square by 12, that will be equal to minus 106.67 kilonewton meter. Next, MFBA is calculated by using plus WL square by 12, that will be equal to plus 106.67 kilonewton meter. And BC is subjected to a central point load. Therefore, MFBC is calculated by using minus WL by 8, where W is the magnitude of the point load and L is length of the member. So that will be minus 60 into 4 by 8, that will be equal to minus 30 kilonewton meter. Next, MFCB is calculated by plus WL by 8, so that will be equal to plus 30 kilonewton meter. Next, to find MCD, so because of this overhanging portion, so this CD member will be subjected to negative bending moment, that is hogging bending moment. So CD is subjected to a point load at the extreme end. So this point load will induce a hogging bending moment. So therefore the sign convention what we follow for hogging bending moment is this one. So at the left end an anti-clockwise couple and at the right end an clockwise couple. A clockwise couple has to act so that the beam will be under hogging. So therefore C is the left end. So at the left end we have a moment in the direction of anti-clockwise. So therefore the magnitude of moment for MCD will be negative because it is anti-clockwise in direction, therefore negative. So negative, and the magnitude is load into distance. Load into distance, that is equal to minus W into L, where W is the magnitude of the load and L is length. So this minus is because of this hogging direction. So C is the left end, therefore at the left end we have anti-clockwise couple, therefore it is minus W into L. So that will be equal to minus 20 into 2, that will be equal to minus 40 kilonewton meter. So that is the calculation of fixed end moments. So only addition is we have to find the moment at the overhanging portion. So next step is to find the distribution factors. So it is calculated in the form of a table. So it is calculated only for the intermediate joints. So in this we have only member joint B as the intermediate joints. C is not an intermediate joint. This is the extreme support. We don't have any support beyond C. Therefore, only B is the intermediate joint for which we have to find the distribution factors. So let us find the distribution factor for joint B. Okay, so the table is prepared as usual. The first column is joint, member, relative stiffness, total stiffness, and then distribution factor. So the joint is joint B, intermediate joint is joint B. So members meeting at joint B are BA and BC. So let us find BA, relative stiffness for BA. So since A is fixed, the far end A is fixed, relative stiffness is calculated by I by L. So that will be equal to 2I. The relative stiffness moment of inertia for member BA or AB is 2I. So 2I divided by length is 8 meters. So that will be equal to 0.25 I. Next member at joint B is BC. So since Far end C is a simple support. Relative stiffness is calculated by 3/4 of I by L. So let us substitute the values. 3/4 of I by 4, that will be equal to 0.1875 I. So total stiffness is summation of relative stiffnesses of the members meeting at a joint. So the total stiffness is 0.25 I plus 0.1875 I, that will be equal to 0.4375 I. Therefore, the distribution factor for BA is the ratio of relative stiffness for BA to the total stiffness at joint B. So 0.25 I divided by 0.4375 I, that will be equal to 0.571. Okay, and distribution factor for member BC is the ratio of 0.1875 I divided by 0.4375 I, that will be equal to 0.429. So this is the distribution factors for members BA and BC. So next step is the distribution of moments. So it is calculated in the form of a table. The first column and the first row we have joint. So different members of the different joints of a member are joint A, B and C. Okay, and for members meeting at different joints are mentioned in second row. For member A, it is AB member, and at B we have got member BA as well as BC, and at C, CB and CD are the members meeting at joint C. Next we have distribution factors. Distribution factor for BA is 0.571 and that for BC is 0.429. So for C it will be, there will not be any distribution factors. Next, fixed end moments. MFAB minus 106.67, MFBA plus 106.67, MFBC minus 30, MFCB plus 30 and MCD is minus 40. So now, as in the previous cases, we will be balancing the intermediate joints, and in the last session we have taken a continuous beam with a simple end, in which we have balanced the extreme simple end first. So in this case also, wherein a continuous beam with the overhang portion is given, we have to balance the joint where the overhanging is given. Okay, so in the given problem, CD is the overhanging portion. So this moment we know, so this is the final moment at CD. Okay, so joint C should be balanced first. So to balance joint C first, this moment is fixed because of the overhanging portion and the load on the overhanging portion. So this value is fixed. Only thing, we have to balance joint C by modifying CB. So how to balance joint C means, summation of moments at joint C should be 0. Therefore, if this is minus 40, so to make it as 0, we have to add plus 10 so that we can make it as plus 40. So plus 40 minus 40, that will be 0. So as soon as you apply a moment of 10 at CB, half of the moment will be carried to the far end from CB to BC. So half of 10 is 5. Okay, so now we have carried from CB to BC, and now let us take a total at this level. Let us make a total at this level so that joint C is balanced. Okay, so now at A we have minus 106.67, at BA plus 106.67, and BC minus 30 plus 5, so it will be minus 25, and at CB 30 plus 10 is 40, and CD it is minus 40. So now joint C is balanced. Only thing, we have been left with joint B. So next is balancing of joint B. So let us balance joint B. So the imbalancing moment at joint B is 106.67 minus 25. So that will be equal to plus 81.67. So the imbalancing moment at joint B is 81.67. Therefore, the balancing moment will be minus 81.67. Minus 81.67 into distribution factors multiplied with the distribution factor, so that this minus 81.67 can be distributed among the members meeting at joint B. So minus 81.67 into 0.571 will be equal to minus 46.633, and minus 81.67 into 0.429 will be equal to minus 35.036. That is balancing of joint B. Next, as soon as you balance joint B by applying minus 81.67, so some portion of moment at BA will be carried to the far end AB. So half of minus 46.633 will be carried to AB, that is minus 23.316. Next, further we don't have any joints to balance. We have already balanced joint C and now we have balanced joint B, and further joint B is not imbalanced by any other carryover moments. So therefore we can stop at this stage and we can get the final moments. So final moments are calculated by adding all the values from the total row. Okay, so add all the values in each column from the total. So minus 106.67 minus 23.316 will be equal to minus 129.986, and plus 106.67 minus 46.63 will be equal to 60.03. Minus 25 minus 35.036 will be equal to minus 60.036. So you can observe joint B is balanced, plus 60 minus 60, and now at C we have plus 40 and minus 40. So now all the joints are balanced. So further we can move ahead to find the support reactions using these end moments. So using these support moments, we'll proceed to find the support reactions. So next step is to find the support reactions. So each support reactions are calculated by considering each span separately. So first let us consider AB member. So AB member is subjected to UDL throughout of intensity 20 kN per meter. So end A is fixed, therefore HA is represented, and with the end moments MAB is minus 129.986, therefore anticlockwise, and MBA is plus 60.037, therefore clockwise. Okay, so let us apply the three equilibrium conditions. So the first equilibrium condition is sigma Fx equals 0, which implies HA is equal to 0. Next, let us apply sigma Fy is equal to 0, which implies VA plus VB1 is equal to 20 into 8, that is equal to 160 kilonewton. Next, take moment of all the forces about A and equate it to 0, which implies minus VB1. So this is inducing anti-clockwise moment about A, therefore minus VB1 into 8, and then this UDL is inducing clockwise moment about A, therefore plus 20 into 8 into 4, and then plus this clockwise moment of 60.037 and minus this anti-clockwise moment, that is 129.986, that is equal to 0. This implies VB1 is equal to 71.25 kilonewton. Therefore VA value will be 88.75 kilonewton. So that is for member AB. Next we will consider member BC. Member BC with the overhanging portion we will consider member BC. So BC is subjected to central point load of 60 kilonewton along with a point load at the end D. Okay, so when we consider this overhanging portion, no need to consider the moment at C. Okay, so that moment will be considered by using this by considering this overhanging portion. Okay, so only we have to consider the moment at the joint B. Okay, so since it is negative, we have represented it in the anti-clockwise direction. So let us consider the equilibrium condition of sigma Fy is equal to 0, which implies VB2 plus RC is equal to 60 plus 20 is equal to 80 kilonewton. Next, apply sigma mb is equal to 0. That means take moment of all the forces about B and equate it to 0, which implies minus RC. This is inducing anti-clockwise moment about B. Therefore, minus RC into 4 plus 60 into 2 plus 20 into 6. And then minus 60.036 will, that is equal to 0. So that implies RC is equal to 45 kilonewton and VB2 will be equal to 35 kilonewton. So total reaction at B, RB, is equal to the summation of VB1 plus VB2, that will be equal to 71.25 plus 35 will be equal to 106.25 kilonewton. So using these reactions we will plot the shear force diagram. So next step is to plot the shear force diagram. To plot the shear force diagram, consider the given beam with the reactions and loading. So reaction at A is 88.75, at B it is 106.25 and at C it is 45 kilonewton. So to draw the shear force diagram, let us draw the baseline of same length as that of the given beam. Let us calculate the shear forces at left and right of each points. Shear force to the left of A, it is 0, and then shear force to the right of A, we have an upward force of 88.75. Therefore, mark it above the baseline for 88.75 kilonewton. Next, shear force from right of A to the left of B, we have a UDL. So therefore, this intensity into load has to be deducted from this one. So 88.75 minus 20 into 8 will be equal to minus 71.25. So mark this ordinate as minus 71.25 and join these 2 points with the linearly varying straight line, linearly varying line. And then shear force to the, this is left of B, the minus 71.25. Next, shear force to the right of B, we have an upward force of 106.25. Therefore, minus 71.25 plus 106.25 will be equal to plus 35. Okay. So, shear force, let us consider this as point E. So, shear force to the left of E. So, in between right of B to left of B, E, we don't have any loading. Therefore, shear force will be constant in between B to C. Sorry, B to E. Next, shear force to the right of E, we have a downward force of 60 kilonewton. So, plus 35 minus 60 will be equal to minus 25. Plus 35 minus 60 will be equal to minus 25. Now that is the shear force to the right of E. Next, shear force to the left of C. Okay, since there is no loading in between right of E to left of C, the shear force variation will be constant. Next, shear force to the right of C, we have an upward force of 45 kilonewton. So minus 25 plus 45, that will be equal to plus 20. Plus 20. Okay. So that is the shear force to the right of C. And then shear force to the left of D. So in between right of C to left of D, we don't have any value. So shear force will be constant till that level. And then shear force to the right of D, we have a downward force of 20 kilonewton. Therefore, the magnitude of shear force to the right of D is plus 20 and then minus 20, that will be equal to 0. So always the shear force should come back to the baseline. So positive shear forces are drawn above the baseline and negative shear forces are drawn below the baseline. So this is the shear force diagram. Next, we will plot bending moment and elastic curve. So to draw the bending moment and elastic curve, consider the given beam. Okay. and along with the support moments. Okay, so for AB member, MAB is 129 minus 129.98, therefore anti-clockwise, and for BA, MBA plus 60.03, and for BC member, MBC is minus 60.03 and MCB is plus 40, and for CD member, MCD is minus 40. So these are the support moments using which we will plot the support moment diagram. To draw the support moment diagram, consider a baseline of the same length as that of the beam. Okay, use the thumb rules to draw the support moment diagram. Left end, left thumb, and right end, right thumb. So the direction of thumb at the left end is moving in the upward direction. So mark it above the baseline for 129.98 kilonewton meter. Next at end B. So B is the right end. So the direction of right thumb is in the upward direction only. So mark it above the baseline for 60.03 kilonewton meter or 04 kilonewton meter. So same point can be considered for BC member as well. At B again this left thumb is moving in the upward direction, so same value, same point. And for CB, right thumb, use the right thumb. So right thumb is again moving in the upward direction, so mark it above the baseline for 40 kilonewton meter. So join these 2 points with the straight line. So this is 40. Next for CD member, C is the left end, so left thumb again moving in the upward direction, so the same point holds good. And at C and at D moment is 0, so therefore we will join from 40 to 0. This is the support moment diagram, over which we have to superimpose with the free bending moment diagram. So free bending moment diagram for AB member is a parabola because it is subjected to UDL throughout. It's a parabola whose magnitude, highest magnitude is calculated by using WL square by 8, which will be equal to 160 kilonewton meter. Okay, and this ordinate will occur at the midspan. BC is subjected to central point load, therefore the variation of free bending moment diagram is a triangle with the highest ordinate as WL by 4, which will be equal to 60 kilonewton meter. So W is 60, L is 4 divided by 4, that will be equal to 60 kilonewton meter. And CD, so this point load, so this moment we have considered already while calculating it. So this is already there. The free bending moment diagram as well as support moment diagram, they are the same for the overhanging portion. So this is the bending moment diagram. So the points where negative and positive moments cross each other, they are called as points of contraflexure. The above portion, so the positive bending moment will be above this support moment diagram, and at supports we have got negative moments. Okay, so this portion gets nullified. Okay, so this is the bending moment diagram. So next, to plot the elastic curve, consider the given beam without loading. Okay, so draw the elastic curve as the variation as that of the bending moment diagram. So negative, so since it's a fixed end, it has to be straight for some portion, and then positive moment dominates, therefore it has to deflect in the downward direction. And at supports, negative moments dominate, therefore it has to be hogging in the supports. Okay, so this is the variation of elastic curve. So this is how you should solve a continuous beam with the overhanging portion. The only thing, you have to balance the overhanging support first or overhanging joint first, and then go on balancing the intermediate joints. This is for today's session. Thank you.